1, go.
Action potential by Brooke Hanson. Action potential is a change in electrical potential between the inside and outside of a nerve. This is essentially what transmits nerve signals. Action potential occurs in excitable cells, which are cells that are able to produce and respond to electrical signals. Excitable cells include neurons, muscle cells, and endocrine cells. Action potential begins at resting membrane potential, which is -70 millivolts. At resting potential, there are more sodium ions outside of this neuron and more potassium ions inside. The membrane permeability of a nerve cell is semi-permeable. This membrane allows some ions to pass through freely, such as water, and blocks the passage of other ions. The channels where ions pass through are called voltage-gated channels. There are two types of channels: voltage-gated sodium ion channels and voltage-gated potassium ion channels. There is also a sodium-potassium pump in the membrane which pushes sodium ions into the cell and potassium ions out. In the intracellular fluid of the neuron, the cell has a strong negative charge. The extracellular fluid outside the cell contains mostly sodium ions, which are positively charged. When the axon is at rest, the sodium-potassium ion pumps keep sodium out and potassium in. For every 3 sodium that go in, 2 potassium go out. When the cell is stimulated, the permeability of the membrane changes, causing the activation gates on the sodium channels to go from closed to open. This rush of sodium ions into the cell is known as influx. The influx causes depolarization and a positive moving change. When the depolarization caused by an influx of sodium ion reaches a critical level between 55 and 60 millivolts, the sodium threshold will have been met. This leads to the initiation of an action potential. Once the action potential has been initiated, the rising phase begins. The rising phase is known as a positive feedback because the voltage-gated sodium ion channels go from slightly open to fully open. This stage of depolarization will continue and sodium ions will rush into the cell until the membrane potential reaches positive 30 millivolts. The refractory period occurs here in this stage. This is where the membrane cannot respond to any further stimulation because a current action potential has reached the threshold and been initiated. Next is what is referred to as the falling phase. Once depolarization has hit positive 30 millivolts, the falling phase begins. In the falling phase, the inactivation gates on the sodium channels close, blocking the sodium ion influx. Repolarization occurs and the activation gates on the potassium channels open. This allows an efflux in which potassium ions diffuse out of the neuron. As potassium ions leave the cell, the membrane potential is returning to its resting state. The charges of the intracellular and extracellular fluid begin to change as the potassium ions leave the neuron. The repolarization typically overshoots the rest potential, causing hyperpolarization. This is when the transbrain membrane potential reaches -90 millivolts. Hyperpolarization prevents the neuron from receiving stimulation from the opposite direction. The cell will then compensate and return to the resting potential where it is ready to receive another stimulus.